We are Group 5, and this is our final presentation for the self-sustaining hydroponic greenhouse with photovoltaic power and optical sensing. Over the course of this project, we were motivated by one primary thing, and that was to eliminate food security in municipalities through the development of an automated hydroponic greenhouse that could function as a community garden. In order to do this, we needed to eliminate three major problems that inhibit the development of community gardens, including the lack of knowledge, the lack of people or volunteers, and the lack of resources, all contributing to an inefficiency that often contributes to the failure of community gardens within cities. We have therefore set out to develop a self-sufficient hydroponic greenhouse that requires minimal human contributions with affordable fixed low costs and low variable costs. And here you can briefly see some of the core advanced and stretched goals and objectives kind of separated out into the different subsystems that we've included here. With this slide being a continuation from the last slide, concluding all of the goals and objectives that drove the design and construction of this system. We then took those goals and objectives and turned them into actionable specifications shown in the green table on the left. We've highlighted for you some of the key specifications we're going to be going over the course of this final demonstration. The first being the boot time of the overall system on the PCB. The second being a plant profile set by a user to automate the greenhouse. We'll then demonstrate that the ECTDS sensor and pH sensor were able to balance the water within those ranges set by a user. And of course, we'll also go over the spectrometer and the wavelength we utilized within the Raman spectroscopy to analyze the overall quality of the water coming out of the filtration system. In this case, it was a 785 nanometer Raman spectroscopy source that we were utilizing to do that analysis. On the right, you're able to see the system functionality and decision matrix that the system will take to automate itself over the course of its operations. So the energy is supplied by those solar panels, and we can see exactly how the water is going to travel from rain into the plant system based on two major decisions: whether the water level is low in a subreservoir and whether that water is balanced in the subreservoir. This will trigger the central reservoir, the filtration system, as well as the nutrient and pH deposition system to ensure that all of the water getting to the plants is proper and well suited for their optimal growth. Here we show you an overall block diagram of the greenhouse system, including the many subsystems and components we've included to make sure it is fully operable.
In designing our rainwater collection system, we stayed pretty faithful to our original drafts of our drawings. As you can see, we have three containers all connected to allow even flow in and distribution of water into the system, as well as a submersible pump and a float sensor. In our final rendition, as you will see, we decided to use a diaphragm pump instead of a submersible pump, but all other pieces remained mostly the same. So here's our rainwater collection unit. It's composed of three containers to store the water that's all being fed by two gutter channels located on the side of the greenhouse. A 3D printed mesh filter prevents lots of the larger particulates from entering into our water storage. We have the system monitored by a float sensor to let us know if it's ever running low on water to ensure that we have time to supplement our own water in this case. All of these containers are being connected underground through PVC to ensure that they're properly being filled and dispersed into our systems evenly. Water from the rainwater system is then filtered and delivered to its respected unit. During this process, water is primed and sent through a diaphragm pump triggered by the system when running low on water and powered through a relay. This pumps the water through a fine mesh filter and then through a sediment filter. We then have it set up to go through three different carbon filters to ensure purity of water and through a UVC tank to ensure the water is at its purest form before diluting it with different pH and nutrients required by the plants. A solenoid is also added to pump to a specific system once all three systems are finally built. Since we wanted to use spectroscopy in our water analysis system, we had to compare infrared spectroscopy, fluorescence spectroscopy, and Raman spectroscopy to decide which would be most beneficial for our system. Fluorescent and infrared spectroscopy were determined to be insufficient for our system, as seen here. We decided to use Raman spectroscopy in our system for many reasons. For one, scattering is less likely to occur when performing Raman spectroscopy than that of the other forms of spectroscopy. We also didn't have to intentionally add impurities into our water like we would have with fluorescence spectroscopy. Raman also allowed us to analyze the water dynamically as it was moving throughout the system directly in line. We use Stokes-Raman spectroscopy, which basically entails a shift in wavelength by the loss of energy in particles and molecules colliding with photons. For our excitation source, we decided to use near-infrared light because it would be best for our inline water system. Here's what our initial spectrometer setup entailed. Two fibers leading to free space, passing 785 nanometer light through a water sample using a bandpass filter and a long pass filter, and lenses to focus the light through the water sample and then into the spectrometer. We had initially included these filters as to prevent light from outside sources contributing into our spectrometer's reading and skewing the results. As we were initially setting up and testing our lens designs, these long pass filters and band pass filters were crucial to prevent outside light from getting into our system. We originally tested our design using a white light source passed through a band pass coupled through the water and then into a stellar whiz spectrometer. This setup alone is not capable of Raman spectroscopy. However, it was very beneficial for seeing our lens design at work. This also inspired us to design and create our own housing for the lens and the fibers to connect up to increase portability of the system overall. Our final rendition of the Raman spectrometer included a 785 nanometer laser excitation module running off of a custom 5-volt power supply. This laser light is coupled into an FCPC fiber, bringing the light as free space into our lens system using bulkheads. Light is sent through nutrient density filters, however not long pass and band pass filters, because the need for these were completely removed with our custom 3D printed housing because of the reduction of outside light interference. Light travels through our lenses, focusing the light into water in our dynamic inline water fittings, and then it travels to SMA cable leading to our Raman spectrometer lent to us by Ocean Insights. This setup allowed us to view the resulting spectrums anywhere along the system because of its greatly improved portability. For water analysis, we used OceanView, which allowed us to use the Raman settings and remove light and dark spectrums through subtraction. We were able to confirm our 785 nanometer laser light by viewing the clean spectrum through air to confirm its wavelength. In Raman spectroscopy, the change in energy of light is the main difference. You can use these resulting spectrums by recognition of molecular function groups which appear at different Raman shifts. This allowed us to confirm the purity of the water through the filter by comparing the baseline to that of a known clean water sample.
One of the key design features of this system is the inclusion of a system-specific reservoir designated to each hydroponic system located within the greenhouse. In the case of a completed greenhouse, there would be 3 of these sub-reservoirs designated to each one of the 3 nutrient film technique systems located inside of the housing. Comprised of 2 separate containers, each sub-reservoir is connected at their base for an equal distribution of water to create a naturally circulatory design where one container acts as an input container, taking in all recycled solution, all new solution, and all new water to keep the water level balanced. The other container instead acts as an output container, which senses all of the water levels, including the physical level of the water, the electroconductivity and total dissolved solids within the water balance, as well as the pH balance of the solution. This water is then pumped into a nutrient film technique system before collecting back into the other container to create that full cycle. Depicted on the right is one of our early designs of what this system-specific reservoir might have looked like. In the case of this design, it would have featured nutrients being pumped in at the base as well as sensing occurring in the input canister. However, we determined that by having all of the sensing occurring in the output can, we would be able to more easily determine if there was a proper cycle of water occurring. So we invented a small buoy system using pool floaties and PVC and attaching the sensors and pump to this buoy so that all of the sensing and pumping was occurring at the top of the output canister. This allowed us to more easily determine whether or not a circulation of nutrient and pH solution was occurring. Following the Raman spectrometer is the system-specific reservoir. In the video on the left, we're showing how when we update the system with a new plant profile, it immediately triggers the output can on the left-hand side, which is pumping that nutrient and pH balanced solution into the nutrient film technique system. On the right-hand side, that is showing the inside view of the greenhouse immediately after we triggered the system. You can also see here how the water is recycled back into the sub-reservoir. Each specific reservoir will feature an ECTDS sensor, an optical pH sensor, a water level sensor, a submersible water pump, and featuring a naturally circulatory design in which the right can acts as an input and the left can acts as an output, so that as the water pumps into the nutrient film technique system, it comes back down into that right side and flows underground to create one full cycle. We can also see the peristaltic pumps pumping in balancing solutions.
When our system sensors detect that our pH or nutrient levels are out of range, peristaltic pumps add solution to bring our values back into our specified range. Each solution being added also has a float level sensor, which will provide a signal to our microcontroller that the solutions need to be refilled. Our EC/TDS sensor has a range of 10,000 parts per million, which is more than enough for hydroponics. These sensors are responsible for reporting levels to the microcontroller, which then evaluates the levels. Our pH sensor has the full range of pH 0 to 14. This sensor functions similarly to that of the EC/TDS. Peristaltic pumps are powered for 20 seconds whenever the sensors report invalid levels. This adds about 33 milliliters of solution to the subsystem reservoir.
There are many different forms of hydroponic systems. For us, we identified nutrient film technique as the most beneficial. For our initial hydroponic system, we designed a 3-layer, 2-row system. To ensure enough space for the plants to grow properly, we reduced this later to a 2-layer, 2-row system. This NFT system was mostly gravity fed to reduce the need for extra pumps. So here's our hydroponic structure. It's a nutrient film technique structure. Water from the sub-reservoir is being pumped into the system, already pH and nutrients balanced, and then water is cascaded down the 2 levels, supplying the plants with the proper nutrients and pH needed, as well as water, to ensure great harvests for us. After this, the water is then taken out of the system, back into the container to be rebalanced and used again to the plants. We made sure that the dimensions of this hydroponic greenhouse were in our specifications to ensure that we had enough space to fit 3 of these whole systems inside of our greenhouse once everything's completed.
Greenhouse wouldn't be complete without our photovoltaic power generation system, in which we feature 2 100-watt monocrystalline solar panels attached to a hand-constructed frame along a 30-degree angle relative to the ground. We have that passing through a solar charge controller to regulate and monitor the amount of charge we're getting into a 12-volt DC battery. And that DC battery also features an AC inverter on there as well for some of our AC necessary power systems, including the UVC filtration system. And then in order to bypass the circuit, we also used a relay that's attached directly to the battery. The purpose of this relay was to solve one of the problems we encountered in the design of the system. Unfortunately, we weren't able to use the same submersible water pump we used in the sub-reservoir for our central rainwater collection unit. This was because it wasn't able to get enough PSI through the filter in order to pass over to the sub-reservoir, so we switched to that diaphragm pump. That diaphragm pump unfortunately required a much larger amp draw than what the submersible pump needed, so we incorporated this relay to trigger from the battery instead of from the PCB to bypass the need for a higher amperage. We also included on this power unit a voltage regulator so that we could regulate the voltage coming from the battery as well as putting an amperage into the system as well, so that we knew that we had a 4 amp limit as well as the 12 volt supply going into our power. Shown here are the 2 designs that we could have gone with the photovoltaic system. We opted for the left design, which is a picture of our current solar panels set out behind the greenhouse. This is that 30-degree angle mount like we discussed just a slide before, and those are the 2 100-watt monocrystalline solar panels. On the right was a concept design for what would have been a solar tracking photovoltaic system, which we would hope to be able to design in the future for future systems to optimize that power generation.
Here we have the control system block diagram for our project, including the sensors and pumps, as well as a 12-volt supply coming from our photovoltaic system. We will begin by taking a look at our 3.3-volt regulator. All of the devices connected to our 3.3-volt supply will source roughly 739 milliamps. For this reason, we looked for a regulator that could support at least 1 amp. We compared two parts that had very similar attributes, with the TPS coming out above with its 95% efficiency, as well as its lower price point. Next, we have our wireless communication. Wireless communication is needed to connect our user's device to the control system. We looked at two different technologies when selecting wireless communication for our project, Wi-Fi and Bluetooth. One of the main factors when selecting our wireless technology was accessibility. Wi-Fi capabilities are available in most laptops, phones, and tablets, which made it a prime candidate. The main downfall to our selection is that Wi-Fi has a higher current consumption as compared to Bluetooth. The Wi-Fi modules we compared were the ESP01S and the CC3100. Both modules perform almost identically to one another. The ESP01S was chosen due to its ease of integration with the PCB, as it is a dual inline package. We also chose this module due to the abundance we already had. The brain of our control system is our microcontroller. The microcontroller is responsible for gathering and responding to sensor data. The microcontroller also communicates with the Wi-Fi module using UART to provide sensor data and plant profiles. The microcontroller stores critical data such as plant profiles into flash, so this data is not lost if power is lost. Our main focus when looking for a microcontroller was a low current consumption, large number of GPIOs, and a decently sized non-volatile memory to store data. We selected the MSP430 FR2476 because it met all of our criteria. This microcontroller is also available in a development kit, enabling us to prototype quickly. Next, we will look at our sensors, pumps, and their additional components. As we progressed through our project, pins began to dwindle quickly. In an effort to anticipate any changes that needed to be made down the road, we decided to utilize multiplexers to conserve pins. There are many comparable multiplexers, but the one we found to be the cheapest that works with our microcontroller's logic levels was the SN74HC151N. This is a 3 to 8 multiplexer requiring a total of 4 I/O pins to implement, 3 selection lines and 1 data output line. Using the same 3 selection lines with an additional multiplexer and adding an additional data output line enables us to further minimize pin use. We require 13 liquid level switches, making this multiplexer configuration perfect for liquid level sensing. The liquid level switches are simple float switches. When the liquid level is high and the top is floating, the switch is open. When the liquid reaches a low level and the top is no longer floating, the switch closes, signaling a low level. To make use of these switches, a single I/O line is placed on the anode of all the switches. This pin must be set to high for the switches to be accurately read. The EC/TDS sensor is used to detect dissolved solids in the plant's water supply. The module we selected was the Atlas Scientific EZO-EC for two main reasons. This sensor can run off the same 3.3 volt supply we already have, and we can chain them together using I2C communication. For pH sensing, we went for a sensor that would operate at 3.3 volts and provide the highest accuracy and range. DF Robot's pH sensor was the best option due to its lower price point as well as slightly higher accuracy and range. The pumps selected for our design require 12 volts to operate and have a current consumption of 250 milliamps. Our microcontroller is unable to provide this output, so drivers must be used to control the pumps. We looked at two separate drivers with almost identical characteristics and selected the ULQ2003AN due to its lower price point. Here we have the overall schematic for our design. The 3.3 volt regulator requires several bypass capacitors to remove any unnecessary noise. Programming headers were added to our microcontroller to simplify programming. The liquid level switches connected to the multiplexers require pull-down resistors as to not leave any input floating. The pH sensors require a voltage divider to make use of the 3-volt analog signal generated from the sensors. Additional headers were placed for our EC/TDS sensors. Headers were also placed for our pumps. The Wi-Fi module requires a boot sequence to be placed into programming mode, which the buttons will be used for. Programming headers were also placed to simplify programming. Here we have our PCB. On the left we have our PCB with all our components installed for a one hydroponic system setup. On the right is a rendered image of the same PCB. The PCB has two separate voltage levels, 12 volts for the power to the driver loads and regulator, and 3.3 volts from the regulator to the remaining PCB components. Looking at the PCB, you can see wire traces with relatively large widths. This is important as we will be pulling up to 1.3 amps of current on those lines. Here we have our two microcontrollers. On the left is our ESP8266 as well as its programming pins, and on the right is the MSP430 as well as its programming pins. This slide shows the liquid level sensing circuit, which includes two multiplexers for pin conservation on the left. On the right we have our connections for our remaining EC/TDS and pH sensors. The pumps are controlled through the use of low side drivers as shown below. Our main microcontroller and our Wi-Fi module's microcontroller both need to be programmed for our system to operate. For programming, Code Composer Studio was used for the MSP430 microcontroller, and Arduino IDE was used for our Wi-Fi module. Here is the software block diagram for our project. The MSP430 is interrupt driven while the Wi-Fi module utilizes polling. For our sensors to perform accurately, they needed to be calibrated using known solutions. Both the pH and EC/TDS sensors use the same slope intercept technique to provide a result to our MSP430 microcontroller. Each sensor was dipped into two separate solutions, with results being used to generate respective slope intercept formulas. These formulas are then taken and used in our system program. Our website makes use of various languages to provide a simple yet responsive website and perform all of the required functionalities. The website has three main views as shown below. The home view shows all the sensor information. The config view shows all the plant profiles and gives you the option to update or remove them. The edit view is where the actual editing of the profile occurs. The images also show the slight difference in mobile and desktop appearance.
Our budget for this project ended up being rather expensive for its entirety, so an entire system, if we were to go ahead and reconstruct this whole thing with all the tools we have now and all the knowledge we've gained, it would be about $5,000, but in total spending that we've had on this current system, we are up to $3,675, which includes all the costs of all the tools and materials, all the mistakes we made, that sort of thing. The expected cost of the total system, including all of our mistakes and then the additions to make a full 3 hydroponic system greenhouse, including the sub-reservoirs and nutrient and pH deposition systems, is expected to be a little bit above that $5,000. So any groups or municipalities that would want to go ahead and build this sort of thing on their own in the future, it would cost them somewhere around $5,000 or just under in order to be able to go ahead and have this sort of community garden. Thankfully, that cost was able to be mitigated in part by the Oviedo Historical Society, who, on top of their monetary donation of $1,500, they also gave us the spatial donation at the Lawton House Museum located in Oviedo. So the Oviedo Historical Society is our primary sponsor for the project, and once this project is completed, following the conclusion of senior design, we'll complete the system to actually function as a community garden within the city of Oviedo, and it will be continued to be run and monitored by the Oviedo Historical Society. The optical system, the Raman spectrometer and laser module, were loaned by Ocean Insight, and they are now being used and employed in the current setup, and they'll be returned following the conclusion of the project, whereas the fiber optic cables were loaned by Dr. Correa, and that was the FCPC to FCPC and the SMA to SMA fibers that are used for the Raman and the laser module. Finally, the cost as shown in the budget is currently lower than what the expected final cost for the entire system is, because we focused on doing a proof of concept for the Oviedo Historical Society using one hydroponic system, and so we'll go ahead and finish that out with 2 more hydroponic systems after the project is completed, so that the greenhouse can be done and functioning for the city of Oviedo. As we come to the end of this curriculum, we're looking back and we're kind of assessing the work that has been done as well as the future work that we're able to do. When we started this project, the goal was to be able to design a community garden that could function mostly on its own without the need for any outside resources in order to make it operable. This was in turn supposed to combat the growing problem of food insecurity within municipalities, so that any food insecure individuals, any individuals that are impoverished, anyone that may find themselves down on their luck and unable to purchase affordable organic foods would have a viable solution coming to their communities sometime in the near future. We were able to prove throughout this process that we could eliminate the need for people, resources, and knowledge to make this possible. Throughout the course of this demo and as well as the final presentation, we've been able to showcase that we have a very fast boot time for our system. The budget comes in relatively cheap at around $5,000 for what this system is capable of doing. We were able to show that based on a profile, we can have a specific sensitivity for our TDS sensor as well as our pH sensor that's able to balance the solution of the water for our nutrient film technique hydroponic system. That system itself is able to house 36 plants and fits within a 22 by 65 by 65 inch space. We have a relatively low power consumption, all generating positive power from a photovoltaic system, and we are able to house 3 systems inside. The photovoltaic, of course, powers that 12-volt battery, and we used that spectrometer at a 785 nanometer wavelength showcased earlier in this presentation as well. As we continue to move forward and look towards what this greenhouse can be done for this greenhouse in the future, as well as how we would be able to upgrade the greenhouse, we know that optimizing the system and making it a little bit more efficient to reduce that cost would make it even more viable for nonprofit groups to be able to use. We would love to see 2 more reservoirs and hydroponic systems installed following the conclusion of this project, and that would allow us to increase that plant diversity. Improving the weatherproofing conditions is definitely a must for any future systems. That would be, better framing, more fencing, something that allows for a better rooting into the ground. And finally, we think that we'd be able to do that most effectively by hand constructing the greenhouse as opposed to using a kit. This would also allow us to create better plant capacity within the system. Simply by adding 1 extra foot in height could allow us to increase the plants by over 50. So we have a lot of potential solutions going forward and a lot of ways that groups and cities could improve this system within their own localities.